Oh, hello. Hi, everybody. Happy Friday. Yes, we finally made it to Friday. Woo! Um, yeah, I don't know. This week was good. I had a good week. Last week was good too. Oh, hello. Happy Friday. Ah! I guess we're gonna do some more. We're gonna do some more hacking on TenderJIT today. I made a few slides so we can like look at it, but maybe I'll wait. Maybe I'll wait a little minute, a little bit before starting. Hello, hello. I changed my setup a little bit today. I have an iPad, so I normally have my computer over here, and I can't really see anything. Um, but I put an iPad down here so I can see the chat while I'm typing stuff in. I guess let's start. I suppose. I mean, why not? Okay, let me hit play on the keynote. Let's see. Keynote. All right. Welcome to the Cool Stuff live stream. Woo! I love cool stuff, and we're going to talk about cool stuff today. We're going to do some TenderJIT hacking. Yeah, that's what we're going to do today. Just hack on some TenderJIT. Let's see. Oh, happy Friday, everybody. Happy Friday. I prepared this presentation earlier today, and I haven't practiced it whatsoever. So please forgive me if it's not super well polished. So last week was Thanksgiving. I made a lot of food. I ate a lot of food, and it was a good time. I made a pie. So I made all this stuff. I made a pie. Like here's a pie I made, and then I made a turkey. And right here is some jam that I made too, and it was good. I saw Evan. Hi, Evan. He's probably not watching, but I'm saying hello to him. I went to lunch with Evan. It was nice. I also got this in the mail, which I'm really excited about. It is called the Dev Term, an open source it is an open source portable terminal. And you should check out clockworkpi.com. Like these things were amazing. I'm gonna put it together. I'm gonna put it together tonight, and I'm really excited about it. It's basically just it's a Raspberry Pi basically, but it's got this cool thing like a LCD display. It looks pretty awesome. So you should check that out. I'm excited about that. Oh, I made this project. It's called Asmreppel, and released that. And I don't know. I thought it was a fun project, so I thought maybe I would share that on the live stream. So yeah, let's do. Okay, I said I was going to do some TenderJIT hacking, but first let's take a look at this. Take a look at Asmreppel, which I really enjoy it. It is a fun project. Let's do. Oh, go back here. I don't care about you, Keynote. So here it is. Basically, what it is it's a REPL for assembly language. Like, I'm not I'm not really confident with assembly language, or I mean, I guess I'm building more confidence, but I feel like when I'm not confident about something, even especially when I'm doing Ruby programming, I like to pop into IRB and just type stuff in, and I think a REPL is so nice. If you like, if you're getting started with assembly language, it's I think it's hard to get started because like you can't just focus on the language itself. You have to learn like how do you assemble things, and then how do you get it running, and there's a bunch of different like boilerplate code that you have to add just to get an assembly language program running when like I just want to learn the language. I don't really care about the boilerplate. I mean, I'll learn the boilerplate stuff later, but like really I just want to do the language. So that's why I wrote this REPL, and I kind of want to show it off. Um, so you have to run, I guess it doesn't support Ruby 2.6, unfortunately. Maybe I got a bug about that. Like maybe I should make it do that, but I didn't. And you have to run it with sudo on Mac OS. And here it is. So basically, like when you start up the REPL, it shows you the CPU state. Like these are all the let's see if I can use this. These are all the oh no, wrong way. these are all the registers, so, and the register values as well. And like this is right here, this is the instruction pointer. So this is where we are, like where we are in the code. And you can do stuff like, okay, let's just do like mov rax 5 like that, and it'll show you like, oh, okay, the register changed from 0 to 5. I probably should make this better, but if you hit enter a bunch of times, it's like not awesome. Whatever. You can do CPU, and it'll show you the CPU state, and you can see here we got 5 in racks, and then you can do like let's just do, I don't know, mov let's see, R8 3, and then we'll just do like add racks R8, and then we can see here like, oh, okay, racks changed from 5 to 8, and then we have, I guess, the CPU changed some flags. So when you use the add instruction, it changes the flags. And I like this. So one of the big reasons I use this is because like I want to do, I don't remember what different instructions do, especially with regard to the flags on the processor. So like if you use the test instruction, for example, let's do like I don't know. So test does a bitwise and, so we can do like test racks 5, and if we do that, you can see like it set these different flags. It set the 0 flag on there, so we know that those are the same. So you can do like a jump. You know that the 0 flag is set, so you can do a jump based on the 0 flag. Yeah, I don't know what else to show about it. Like I added a disassembly thing. So actually, we'll pop in and check out how it works. Like I'll show off how it works. I added a little disassembly thing that shows you all of the instructions that it ran or that you've compiled. This looks like kind of a bug, I guess. Yeah, it's totally a bug. But yeah, we did like mov racks that we did all of these instructions. Yeah, I'll show off just a little bit how it works. Basically, like, let's do lib Asmreppel. This is not the right one. Let's do set. Is it gonna remember that? Nope. Sorry, I'll bump up the font here. Still gotta get this more smooth. So I wrote a parser. Basically, it parses assembly. I wrote a parser for x86 assembly, and like we've already looked at the assembler Fisk because I use that in TenderJIT for making like emitting x86 instructions or encoding x86. But the REPL part I think is kind of interesting. So like I have to switch based on platform. So if it's Darwin, we load the macOS thing. Otherwise, I assume it's Linux. It doesn't. I've not tested on Windows, and I'm not planning on it. Sorry. Anyway, essentially, what it does is it just creates a JIT, like a JIT buffer. So we have some memory, and it creates this JIT buffer, and we fill the JIT buffer with this 1 byte OXCC. And that 1 byte is just int3. So it's, if we saw down here, like it's this instruction. So that sends an interrupt to the like the processor knows to interrupt the process when it hits that instruction. So what else do I have to do in here? Yeah. Like, well, I'll show you in a minute. Down here, if we look at, this is like the starting function. So the way it works is I fork a process. So we fork a process, and then we call trace me, and this function just does, happy Friday. I'm in a small window, Friday hug. So we fork a process, and we call trace me, and this trace me function, it uses ptrace. So it says like, hey, I want to be traced by my parent process. And then it calls this to function on the JIT buffer and enters the JIT buffer. And we did a memset like we did this mem set, so the entire JIT buffer is just filled with int3 instructions. So the whole buffer is just filled with OXCC. Then what we do is we say, okay, we're going to call into that, and as soon as it calls into it, immediately the first thing it does is the CPU just like sends an interrupt, like immediately. So the process just pauses. Then I've got this tracer class that we tell it what PID we want to trace, which is our this child process, and we call wait on the PID, and then we get the state. And I'll pull up the tracer, like the tracer class, in a minute. And we can take a look at that. But basically, like, we get the state. The state is the state of the CPU in the subprocess. So this thing is responsible for getting all the register information and returning it back to the parent process. And then we just like display, like, if this is the first time we open the REPL, we display the CPU state. And then we just have a method here for displaying any changes to the CPU state. So like when you change I wanted it so that, like, you know, when you change something, it just shows you the differences. Like, I didn't want to display every register all the time. Yeah, so then we just like do read input using reline, which is the same thing IRB uses. And then depending on what the input is, like I've got this disasm, which this was a secret function for debugging, basically. So we have that, like, that JIT buffer. What it does is it just disassembles anything we've written to that JIT buffer. And we can read from a register. So this like just reads. Let's put this up again. Okay. Come on. There we go. So we got CPU. We can do like R8, and it'll just read the R8. Read the R8 value. So that's nice. I also added this, which is also a secret function. You can directly set register values. This isn't released yet. So we can say, like, let's set racks to 10, I guess. Racks equals 10. And what this actually does is it forcibly sets the register value in the child process without executing any assembly. So this is also kind of a debug thingy. Okay. Anyway, otherwise, like, we just parse it. We use a run command, and I'm using pattern matching here I'm using pattern matching here in Ruby, and I kind of love it. Like, it's actually really nice. Like, I really like it. Anyway, if we're just running, then we tell the parser, hey, go parse this. Go parse the assembly, and then we assemble it, and then execute it. Well, we say like, hey, I'm gonna set the, like, what does this do? This rewinds the instruction pointer. So the issue is, like, I don't want to get too into the weeds here. Whatever, it's my stream. I'll do whatever I want to. We're gonna get into the weeds. Let's do that. So you see this address here, this RIP. This is the instruction pointer as we're going through the JIT buffer, and you'll see, like, it's at 1, like some number, and then 1. That's because when the CPU interprets the bytes, it hits that 1 byte, the int3 byte, and it stops after it interpreted it, and that byte it's 1 byte. So the JIT buffer actually starts at like 000, but the instruction pointer is at 1 because it read that byte and then it stopped right there. Now what I wanted to do is, like, overwrite that int3, so we can say like okay, I don't know, mov racks 5, and then if we disassemble, well, actually let's do mov racks 10. Yes, this is the legal type of weeds. Disasm. And then we can see, like, we've got mov racks here and another mov here, and we have to be able to rewind the instruction pointer 1 byte so that it'll, like, we want to rewrite what's there and kind of rewind. So it hits that int3 and it stops right after it, and we want to write over that and keep going. So that's kind of what I've been working on. So we want to move rip back by one byte. And then we write the state, like it writes the state back out to the CPU. So it's like, okay, your instruction pointer is actually one byte previous. And that's about it. One thing that's kind of interesting is like, we've got this JIT buffer that has to be shared. So the parent process needs to write into the child process's JIT buffer. And I couldn't figure out like a really good way, like normal ptrace allows you to do that. So the ptrace system call allows you to write into memory of the child process. But I couldn't figure out a good way to do that on macOS. It was not like, it's really hard to use. Ptrace on macOS is extremely broken. It is not like ptrace on Linux whatsoever. So what I did was, it's a huge hack, but one sec, let's take a look. I mean, the whole thing's a huge hack. So, what I did was, where is it? JIT buffer. So we'll create a new JIT. It creates a new JIT, but it sets the memory protection here to share. Oops, let's do this to shared. So you see it says map shared right here. It's essentially just creating shared memory between the parent and child process. So now the parent process can write to the child process's JIT buffer, and they'll both processes will see it, but we don't have to go through ptrace to do that. And I guess like if we were writing a normal debugger, this definitely wouldn't work. But since this is just for like a REPL, we can totally do this because we're forking our own process and doing our own thing in here. Yeah, so these are all, I mean, that's like basically it. This is like, we have this class that gets the thread state. Mac has to use this weird thing that's like, where is it? Sorry, this is hard to read because of the font, but like Mac has to use this mock API thing. Yeah, get the task, like whatever this thing is. It's like not, I don't know. It's not easy to use. It was not easy to figure out. You got to use get state. Like this thread get state thing does it. Ooh, draw there, yeah. And then that gets the state of the CPU, and then like down here we can set the state of the CPU as well. I'm on a branch right now. Right now I don't have the RIP rewinding working on Linux. I'm gonna work on that. Next. But you can do that through, like, it's pretty well documented how to do that. You can do that through the ptrace system call. To be honest, I didn't think it was possible to do on macOS, or at least I couldn't figure out how to do it, but I finally did. Like if we look at Linux, I mean, it's just using, like, it's got this nice thing. It's like, okay, ptrace, get regs. It's like nice. I like that. And then we can say like continue. So this is how we tell the child process, okay, continue. Yeah. So that is Asmreppel. Let's go back to the presentation. Let's see. Yeah, so 2 weeks ago, oh yeah, and if you have any questions about Asmreppel or any of the stuff I'm talking about, put it in the chat. I got the chat down here, so I can quite easily see it now. Let's see, 2 weeks ago, we implemented opt EQ in TenderJIT. And then, like, I don't know if you recall, but essentially this is opt EQ. So if you do double equals, it generates an opt EQ instruction. So this double equals maps to that opt EQ instruction. So that's what we implemented, and then we ran opt caret, and we found that the place where the most popular instruction where we're exiting was on expand array. That's our next target, is to implement expand array. And what expand array is when we do something like this. So if we have like x comma y equals something, that emits the expand array instruction. So that x comma y you'll see right there is expand array. And before we like get into implementing this, I want to talk about the stack behavior, like how this instruction impacts the VM stack. So, oh yeah, my I don't know, my transitions aren't that great. Like I said, I just put these together today. I don't know. All right, so I simplified the instructions here on the right-hand side, and so that it's a little bit easier to read. And what we're going to do is we're going to step through each instruction and see how each instruction impacts the stack. So first thing we do is we run get local on A, and that pushes the value A onto the stack. And we know here from looking at the Ruby code that A is just going to be that array 1 and 2. Expand array is going to pop a value off of the stack, and then it's going to push two values onto the stack. And how do we know that it's two values? I mean, we can know mainly from looking at the Ruby code that on the left-hand side we want two values. And over here in the instructions, you can see we have that 2 as a parameter. So the expand array instruction will take 2 as a parameter and say, hey, we need to push 2 values onto the stack. Then the next thing that happens is we call set local. Set local pops a value off of the stack and assigns it. So in this case, we have x equal to question mark. And then we'll do another set local. We'll pop a value off the stack and we'll set it so y gets set to question. Now we have to figure out like what values to push onto the stack. And if we were to write this like let's say we implemented expand array like this. So we push the array onto the stack. Expand array says, okay, I'm going to pop a value off the stack. I got an array. I'm going to push, happy Friday. I'm going to push 2 values onto the stack. So let's say we decide to implement it like this. We're going to imagine an implementation. Let's say the first thing we do, we're going to do the very naive thing. We're just going to start at the beginning of the array, and we're just going to push values like on. So we'll say like, okay, we'll start at 1, we'll push 1 onto the stack, and then we'll push 2 onto the stack, and we got our 2 values. And then now we're going to do a set local. We'll pop a value off of the stack, and x gets assigned to 2, and we pop another value off of the stack, and then y gets assigned to 1. Now, like, if you're looking at this Ruby code, if you're looking at this carefully, you'll notice that this is actually wrong. I mean, this Ruby code will run fine because x and y, doesn't matter which one is assigned. In this case, it doesn't matter which one is assigned to which. But you can tell here it's kind of surprising. Like, as a Ruby programmer, you wouldn't expect this at all. You'd expect x to be equal to 1 and y to be equal to 2 because we're expanding that array. So we can't just start at the beginning of the array and push all the values on. We have to actually do it backwards. So the way we have to do it is we have to say, okay, we're going to get the local, we're going to expand the array, and we have to start at 2 and then move back to 1, and then pop 1 off, and then pop 2 off, and now we have our values in the right order. So expand array can't just push stuff from the array. It has to push it backwards. And I mean, I don't know about all of y'all, but I'm not a huge fan of iterating over arrays backwards. It's like not fun, in my opinion. So we have another situation here. Let's say expand array is too long. Like, we have 3 values in here and we only want 2. Actually, this isn't a huge deal at all. We just say like, okay, we'll do our normal get local. When we do the expand array, we know we need to start at element 2 element 1 and move backwards, and we do the same thing. So arrays that are too long, not a big deal. We can handle that. Now let's look at another issue. Let's say we have arrays that are too short. In this case, we're just supplying an array of length 1, and we need 2 elements. So of course this code will raise an exception, but I want to discuss like what the instructions actually do. So first thing, we'll push that onto the stack. We'll do an expand array. An expand array in this case has to push a nil first, and then push the remaining element of the array. So we'll call set local with 1, and then set local again will pop off nil. So we have to be aware, like expand array has to be aware of how wide that array is. Happy Friday, Taylor. Good to see you. Woo! So let's get into some more problems, some storage problems. So we're going to discuss embedded objects versus extended objects. Ruby objects, you may or may not know this, but Ruby objects are a fixed width of 40 bytes. So this is in C Ruby and MRI. So Ruby objects are a fixed width of 40 bytes. What that means is, one pointer. Hey Tom, one pointer is 8 bytes. So a pointer is 8 bytes wide, and we have 40 bytes, which means that each object has 5 slots because 5 times 8 is 40. So that's like we can store 5 pointers in any one Ruby object. And this is what the layout of the objects look like. So on the very left, I've put the generic layout. At the header, we always have some flag bits. So it's a bit field of just flags. We store different flags in there. The next pointer is a pointer to the class, like whatever class this object is, we'll point at that. Now, in the case of an embedded array, if you look at this generic layout, that leaves us with 3 empty slots. So we have three slots that we can deal with. So in the case of an embedded array, what we can do is we can say, well, if the array is less than 3 in size, we can just store each element in each of those empty slots. So we'll say, all right, we'll just store each of those there. Now, if the array expands beyond 3, we can't oh, yes, it's not Friday for long. Hi, Ufuk. Hello. If the array expands beyond 3, like we can't store them all in that 40 bytes, obviously. So we have to store them somewhere else, and that makes the array become an extended array. And in that case, we'll store fields and class again. Then we'll store length, capacity, and also a pointer to a buffer. So we'll have some buffer that we malloc allocate, and it'll point off to that buffer. So that way we can store as many elements as we want to. So capacity is essentially the size of that buffer, and length is the number of elements we've actually stored. So Ruby won't, if you add one array, it's not going to increase the malloc buffer just by 1. It'll I believe the algorithm is to double it in size. I can't remember, but it'll say if I need to expand, I'm gonna expand by a bunch and then fill that out. So that's why we have a capacity versus a length. So we have kind of an issue here. With expand array, we got a lot of combinations. We have embedded and extended, and we have arrays that are too short, and we have arrays that are long enough. Oh yes, Ufuk is right. Ruby objects won't be. Cross our fingers, Ruby objects will not be 40 bytes forever. But this is what it is today. So we have these 4 different combinations of cases that we have to deal with in expand array. And actually this isn't 100% true. This is the 4 combinations that we have to deal with in the case that the object pushed onto the stack is an array. So you can do this I guess I don't have any more slides, so let's just get into the code here. If you do where is my other Mac Vim? Let's see. If you do let's bump this up. Okay. So clearly, right here, we're gonna get an expand array. This is gonna give us an expand array instruction, and of course, a could be anything though. right here, I mean, we're passing an array in, but we could pass like true or false or a hash or like whatever you want to. So those four cases that I was showing in the four cases that I was showing in the slides, they're like that's only in the case that it's an array. Uh, Matthew asks, interesting, are they getting bigger or smaller? The answer is we have a team at work at Shopify where I work. We're working on a project called variable width allocation, where we're able to allocate objects of varying size. hence variable width. So they're getting right now our smallest size class is 40 bytes. But I think like long term we'd really like to make Ruby objects. I mean, I'd personally like to make Ruby objects a power of 2 in size, so those would actually be smaller, so maybe 32 bytes. But right now what we've got and landed, it's actually landed in master right now, so you can turn it on and try it out, though it's not, I don't know. Please turn it on and try it out and report any bugs to us. Okay. So anyway, back to this. We have an array here. Expand array. Expand array. Yes. And I guess I don't know if I mentioned this in the slides, but I implemented the embedded case, but only. Actually, let's do. Okay, yeah. So I implemented this case here where they're embedded and they're long enough. Like I did this one. I don't want to do this one yet. These ones seem hard. Let's do this one. We're going to do long enough and extended. Okay. So let's pull up the code. Am I in the right directory? I am. Great. Okay, so right here, this is the compile expand array function, and it's used down here in handle expand array, and this handler gets called when we compile the instruction sequences. So we'll read through the iseqs and say like, oh, okay, I'm gonna emit machine code for each of these instructions. But in this case, like when we handle expand array, we don't actually know what value is coming in here. So we don't know, is it gonna be is it gonna be an array? Is it gonna be a hash? Like what is the type that's coming in? So in order to figure out what that type is, we need to pause the program and say like, hey, I need to check out what this thing is. Like I need to know what type is coming in. So rather than I don't know, like I don't actually know what the alternative is here really. What we do is we say like, okay, we're gonna defer compilation of this thing. So we're gonna wait. We're gonna emit some machine code. And what the machine code will do is it'll jump off into a deferred compiler. Which, if you've watched any of my previous streams, we've done this a few times before. I added some interesting stuff here, like right here. It says like, okay, if you pass in a special constant, like true, false, any type of ints or floats, those things we're just gonna break here. It's gonna like stop execution of the program. But what that means is in this else case, everything else is something that is on the heap. It's a heap allocated object, so we know it's a Ruby object or a Ruby object that's been allocated out of the GC when we hit this branch. So when we hit this branch, it'll come back up in here and it'll compile. Like the first time it gets hit, it'll run this compile expand array function. And the expand array function is able to look at the stack. So we're able to peek at the runtime stack. So we can say like, okay, what is the thing that we saw right here. Like that's what we see at runtime. So we're peeking at the very top of the stack, which we know when we were looking at the stack behavior, we saw that very top thing was the array or whatever type it was. But the nice thing is we know we're never going to enter this function unless it's a heap allocated object. Then down here we check the type. So right now it's only dealing with arrays. So this is essentially our compile time type. So we see like, okay, yeah, let's check the type. The compile time type is an array. So we know it's an array, but we have to verify our compile time. Oh, sorry, there's one more check. Right. Is it an embedded array or is it an extended array? And we care which one is which, because depending on whether it's embedded or extended, we have to read the array values from a different location. So we'll say, okay, if the compile time one is embedded, then we'll take this branch down here. Otherwise, it's not implemented. This actually, I should say like implemented heap extended. Right, so it'll break right there. We'll get an exception. So if it's embedded at compile time, we still have to do a check at runtime. So we have to, any type of check that we do at compile time, we kind of have to repeat that check at runtime in order to verify our assumptions. So like here, maybe we emitted machine code. We emitted machine code here for embedded arrays, but what if the next time somebody called us and the array is not embedded anymore, we need to emit new machine code. So we kind of have to repeat that check. All right. So this repeats the check. It just checks at runtime. Oh, is this an embedded array? If it is, then we'll say like, okay, let's get the length. If the length is greater than or equal to the number that the instruction wanted. So you remember in the slides it showed like, okay, we get expand array with 2, like it wanted 2. If it's greater than or equal to that value, then we'll go ahead and like write out the values of the array. And here I'm doing something that I think is kind of fun. Like it's, instead of writing this loop that reads backwards in assembly, I essentially just wrote the loop in Ruby. I essentially just unrolled the loop here. So we're saying in Ruby we're gonna do like 2 times down to 0, because remember we gotta go backwards through the array. Get a reference, like get the array element here, and then push that array element onto the stack. And if we were able to get through all of that, then great. We'll jump back into the where we came from, and then continue with execution. Otherwise, if it's not an embedded array, like let's say our runtime check failed, then down here we'll just break. We'll stop the program. One thing I kind of want to point out here is like, I don't know if I've discussed this in previous streams, but I kind of want to change the names for these because they're probably not great. But RB, anytime I'm using RB, that's a compile time check. So this is a compile time check. And this RT, which stands for runtime, this is for handling runtime checks, and it's essentially a DSL for producing machine code. And you'll notice here, like I've got these blocks that are like if whatever, and then it takes a block. And if we go look at the end of the block, whatever the return value is, it calls .else as well. So what's actually happening is when this Ruby code is executed, both sides of these branches are evaluated. So when this Ruby code runs, it evaluates this side of the branch and it generates machine code for that. And then it also evaluates this side of the branch and generates machine code for that as well. But the DSL takes care of putting a label and then jumping in case the label doesn't match, or in case the comparison doesn't match. So both sides of these are actually evaluated. Okay. So So let's do something. All right. I guess we're going to do some live coding now, which, yeah, for the next 20 minutes. Okay, so we're going to do this case down here. We have an extended array. So this one. And let's do test instructions, expand array test. I don't think I write. Oh yeah, we're not doing this one. I wrote a test case for when the array is too short. We're not doing that. I don't want to do it. It's not fun. Let's do when the array is too long. So we're gonna do def test. Well, we'll do a long enough. I shouldn't say too long. It's not too long. It's long enough. Test expand array. What do we call it? Like not embedded. We'll say long enough. I don't know. Whatever. So we're gonna call the expand array thing, and we're gonna do it. So what I like to do is I just call it, and then JIT the function. So I call it once with a normal interpreter, get the results from that, so we know that that's our expected behavior, and then JIT the function, and then call the JITted version and verify that the two match. So we'll do this, and we know it needs to be like 3 isn't enough. It's got to be at least 4. So we'll know that this is actually an expanded array or a non-embedded array. And then let's grab this. I don't know if, yeah, okay. Yeah, we'll do that. Let's just copy the whole thing. Oh, so here I should figure out a way. I need to figure out a way to show my keystrokes on in the live stream, which I will figure out how to do that. But if you're inside of a Ruby method, you can do VIM and it'll highlight everything in the method. So I was just doing VIMY and then that like grab the whole thing. And then I can just paste it here. Okay. So we'll put this down here. All right. So we'll just make sure that this works correctly, and it should fail. It's going to give us, hopefully it'll give us an exception. So let's see. Goodbye, Asmreppel. Let's do expand array test. I don't really feel like running it in LLDB right now. I mean, we will definitely run it in LLDB, but not right now. SN, what was the test name? Not embedded long enough. So run this. Oh my goodness. Oh my goodness, we got an exception, which is exactly what we wanted. It says, not implemented error, extended arrays are not supported. Okay, so let's do that. All right. So let's see. We got to repeat our we have to repeat our compile time assumptions. So let's say somebody calls us with an embedded array. So it blows my mind the number of tests that we have to do, because you have to say so we have embedded and extended, and well, we have to test, is it an array? Is it embedded? Is it extended? And we have to repeat all of these tests depending on which branch that we went through, because oh, maybe I got an array at compile time and it was embedded, but now at runtime I got a hash, or now at runtime I got an array that's extended. So it just, I don't know. It's interesting, I guess. All right, so down here we're gonna say okay, if it's embedded, what? No. We know it's not embedded. At runtime, if it's embedded, this needs to break. So we'll break right now, but this should be like a recompile case. So we'll say okay, I got an extended array at compile time, and now at runtime I got an embedded array, and what we'll do is we'll just recompile this case. So we'll say hey, go go generate machine code for the embedded case. So here we'll do our else. This is where we're gonna do like our main work. I think I'm gonna copy. I think what I'm gonna do is basically just copy this stuff. Let's copy this case. Okay, so do it down here, and then we're gonna get. It's not embedded. It's extended. So we got to get the length. We got to get the length of the array. And I'm gonna throw in. What I'm gonna do is I'm just gonna throw in a break right here. I like to throw in a breakpoint and then fire it up in LLDB, and then check what machine code got written out, and make sure that it's doing what I want. So let's actually run. Oh, you know what else I want to do? Let's do Oh, nice. I have tabs up. Oh, this is full screen. This is so nice. This is so nice. This is nice. And it's nice. It's nice that you're all here with me today. Thank you. Let's see. What do I want to do? Runtime, yes. Lib TenderJIT runtime. So let's take a look at the runtime, and I want to add like. So we have this break. This break method just outputs that int3. Like we were looking at that. We were looking at int3 earlier with the Asmreppel. All we're doing here is the same thing. We're just throwing out this one byte, so we get a break. We get a breakpoint. But I want to add I'm gonna add a nop too, just so that we know, like, I don't know. It's like a little breadcrumb, basically a breadcrumb for myself. So I could say like, let's do rt.nop. rt.nop. So when we pull this up in LLDB, we'll expect that there are two nops here, and that's how we know we hit this breakpoint versus this one or this one. So let's do that. So we'll pull this up in LLDB. All right. Clear the screen and then run it. Oh, and I have mismatched indentations. Interesting. Okay. Why is that? Oh, yeah, it's definitely mismatched, but who is mismatched? You know what? Let's delete some of this stuff so we can see better. Just get in here. Yeah, nice. I like that better. It's probably in that stuff I copy and pasted. I didn't copy and paste enough stuff. I didn't copy and paste enough stuff. Yes, I am a trained professional. All right, so let's just make sure that we get into that else statement. So we want to make sure that we get in here. Like, that's what I want to know. Okay? Not here. Otherwise it's a bug. Okay. So let's just rerun. And yeah. Oh. Odd. I'm not sure why we broke. Why it's at that jump. I would expect it to be here. Let's see. Oh yeah, that's not good. Let's see. Why is this? If embedded array stack top. Interesting. Where did we? So we must have broken in here. This must be wrong. Let's put let's do this. Put a nop here and then a break here, and see what this looks like. Yeah, let's see. Nop, break, yeah, totally. Yep. It's going into that, like, it's going in there. Why is that? Let's look at, so what's happening is, like, compile time saw an extended array, and for some reason our runtime is seeing an embedded array, and I'm not sure why. So it could be a bug with our check, or maybe like it's a bug somewhere. But let's look at the stack top. So we know that SP is 1. So TenderJIT stores the stack in register R15 so we can inspect what's in the stack. So let's look. Let's do this. RP. Actually, I think I have this in my history somewhere. Oh shoot, I got a meeting in 10. All right. So that's wrong. RP15, let's look at the 0th element is an array. And this is just an object. Yeah, so I don't get it. That seems like our right thing. Let's go back over here. We'll go into the if embedded array test. Okay. Let's set a breakpoint here. So let's set a breakpoint before we do the test and then check what the values are. So what this is doing is saying, okay, we're going to take the T mask, and this may be totally wrong. Like, I'm not sure if this is 100% correct here, this test that I'm doing, because we have to mask off some bits. Oh, yeah. This isn't going to work, is it? No. Okay. So in order to tell what whether or not it's embedded, we have to mask off the flags and then find the right bit. So this mask gives us just those important bits. The T mask one does, like, this is our mask for it. And then this one is whether or not the flag was set. So I was anding those together to see if I could like make a shortcut, but I don't think this is correct. So let's do this. We're just gonna and off with, what do we want? Right here, we're getting the flags for this object. And then we and the flags and then do a comparison to see if they're the same. I think we're gonna have to do and Ruby T mask. So now the flags register should, what is the nice software that allows you to draw arrows? I'm using, the heck is this thing? It is called ScreenBrush. ScreenBrush, yes. Okay, so we'll and off the mask, and then what? What do we do? Let's look at, you know what? I'm feeling very lazy. Let's go look at Ruby source. Let's see, R array, and I think there's embedded. Array embed P. Let's go check that. FL test raw. So we have to check the flags, and it checks, is this not equal to 0? So it's kind of odd. FL test raw. Okay, let's go find that. Ooh. So it gets the flags. I don't need, okay, if it's just using FL test raw, then we shouldn't need to do that. It's just anding the two, right? And if it's not 0, then it should be embedded. So let's, like, it seems to me that we could just do and Ruby R array embed flag. We don't need to do that. Actually, let's undo this. We'll just do, I think this just needs to be that. We'll do that, and not here, not comp. We need to test, like, if it's 0, we want to jump, right? That's what Ruby was doing here. It's saying, like, and. So if this thing returns non-0, then we think it's true. So we'll do and on the mask. Okay, I gotta think about this. So if it's set, it will be 0. Oh my god. flags and mask. I think we just do test flags dot. No, let's do fisc dot test flags mask. And I think in this case, it'll be like this. The Z flags should be, well, I don't know. Let's just walk through it. Oh, error. Okay. Okay. What did I do wrong? Oh my gosh. Oh my gosh. Okay. Yeah, we got to call to register on this. Okay. Run. Oh my gosh. Why? Oh, right. And then we got to say got to tell it that it's an immediate. Okay. Okay, so let's see. We're doing a mov here from R15 into R9. What is that? That's right here. We're copying from the top of the stack into this register. So that's R9. And then down here we're getting the flags from that object here. So let's take a look. Let's take a look. Oh, where's my tab? There. No. Come back to me, terminal. All right. So we should be able to do like, let's do this SI. That runs one instruction. So we should be able to do RP $R9. And this should be our array. So we should have put the array into the R9 register. And yep, there it is. That is our array. And then we need to do, okay. So then we need to get the flags off of the array. So we could do like p, well, I'm sure this is gonna work, but we could do like p, like let's do struct our basic star $R9. That gives us our pointer to that. So if we look at the flags, so the flags should be 4007. So when we run this instruction, it should put 4007 into R9. So let's do that. SI px R9. And yes, we have 4007 in there. So then we need to do test. And this is going to test. I think this will test whether or not this bit is set. I think. So let's do that. Let's do SI. Okay, so this is where getting back to why I like to use Asmreppel, which we're going to jump into right now. So I don't know what the Z flags are. I don't know whether or not this came back as 0, and because I don't know, not smart enough. Let's see. Let's do sudo this. So we're gonna do like, what do we have? R9 was this number, so let's do that. Mov R9, that, and then we're gonna do test with OX2000. Test R9, that. Oh, oops, yeah. Can't do that. Thank you. Okay, so the Z flag is not set in this case. Okay, so it's not 0. So we need to say, oh, where's Vim? Not comp, J N Z. I think that's what we want. Let's try that. So let's rerun. Okay, SI, doot. And I think this is gonna jump. So let's see, do we go to 167? No. Okay. JZ. Okay, SI, I. That should jump. Okay, it did. And then we've got our int and our 2 nops there. Let's go check our Let's go check Vim. Okay, so here's our we're now in the else case. So our int and two nops. Actually, it's time. I have a meeting now. It's almost time. Let's make sure. Let's stop here, but let's make sure that the previous test works because I am afraid I messed up this. I'm not sure if this conditional is 100% correct, but I do have test cases for this. Like this one's already implemented, so we know that the positive case needs to work. So let's try it. Like, let's just try executing that one and see if it happens. What is the name of the test case? Spew expand array test, and it is this one. Long enough. Let's see if it runs. I think we added a breakpoint, but that's good. Let's just continue. Yeah, okay. So the test still passes. So we did do that correctly. All right, I am going to stop the stream here, and I don't know, go to my meeting. Thank you all for coming. It was really good to hang out on a Friday. And I hope that I will see you all again soon. Bye.